There. I'm recording for Ashley. Now, I don't know if it's going to turn out well because my image got goofy when I did that, but we'll see. Everything's closed except for this. So yeah, okay, so we're recording for Ashley, and for Ashley only. Everybody say hi to Ashley.
Hi, Ashley.
There you go. She's not online. She's just not here because she's a slacker. Okay, so trig identities to know. This one is called the Pythagorean Identity. It is the Mac Daddy of all trigonometric identities. Sine squared theta plus cosine squared theta equals 1. It is the identity. It's the most important one. It's in the reference sheet. Yes?
Tell them why it's called the Pythagorean. Show them like that it's literally the Pythagorean theorem. Like they don't see it yet.
They might.
But just write it down. Why not?
Okay, so it's because it's x. It says, all right. We have a triangle in quadrant 1. And this point up here is x comma y. If this is theta, oh, and by the way, we're calling this the unit circle, so it has a radius of 1. If this is theta, I don't know what happened to my theta, but if you recall, we said that cosine of theta is x over r, so x over 1. So cosine of theta is x. And sine of theta is opposite of our hypotenuse, or y over r, which is y over 1. So sine of theta is y. So instead of saying x squared plus y squared equals 1, we say 1 squared, but 1. We say sine squared plus cosine squared equals 1. There it is. It's just the Pythagorean theorem of the unit triangle in quadrant 1. Boom. Now, tangent theta is sine theta over cosine theta, also in the reference sheet. So the two trig identities that you must know are those two right there. Now we've got a bunch of angle relationships that are true about these things. It's great if you know these, but rarely is it necessary that you know it for IB style questions. Now, I think I've seen some questions where it was helpful to know the things, but it wasn't required. It just was like it got you to an answer faster if you knew some of the things that we're about to talk about. This one right here basically says sine of a negative angle is equal to negative sine of that positive angle. Why is this true? Well, geometrically, because sine is an odd function. So reflecting over the x is the same as reflecting over the y. But if you were to graph this, sine is positive in quadrant 1, right? So if you took this angle but you made it a negative angle, it would come down here. It would be the exact same triangle with a negative angle, only now your y value is negative. So that's why that's true. Now cosine of negative theta is just equal to cosine of positive theta. This one's really easy to see why, because cosine is positive in quadrants 1 and 4. So cosine of this angle gets you positive x over 1. But if you gave it the negative angle, it'd be down here, and you would still get x over 1.
Does that also work the other way, like if would negative cosine theta be equivalent to cosine theta?
No, just this. And another reason why this is true is because cosine is an even function. Reflecting over the x-axis, reflecting over the y-axis is the same as doing nothing. So since sine is odd, this is true. Since cosine is even, this is true. So why is it called cosine again? Do you guys remember? But why is it cosine? Oh, they add up to something, yeah. Complementary. You see, this theta and this angle up here will always be complementary angles. It's called cosine because sine and cosine of complementary angles are equal to each other. So cosine of 50 equals sine of 40. These two identities basically say that. It goes, hey, pi, which is 180. Take your angle, 180, subtract any theta you want from it, as long as it's between 0 and 180, obviously. and you'll get sine of theta again. But why is that true? Well, because that's just saying if you took this triangle and reflected it over the y-axis, you'd get the same sine ratio. So that's all this says. Oh, I'm sorry, I misspoke. When I was talking about the whole complementary thing, that was for the next set. Might be. Anyway, this one's telling you reflecting over the y-axis. So let's just say theta is 20. Let's say this theta is 20. Then I could reflect this triangle to quadrant 2, where it would be still a 20-degree angle inside the triangle, but wouldn't it actually be 160? 180 minus 20. That's why it's the same sine ratio. Now, since cosine is negative in quadrant 2, doing what we just talked about for cosine just changes the sign, S-I-G-N, of the cosine value. So cosine of 20 degrees equals negative cosine of 160 degrees, because in quadrant 2, cosine is negative. Now, to the whole complementary crap. Pi over 2 is 90 degrees. So take any angle you want between 0 and 90 and subtract it from 90, and you get its complement. So sine of an angle is equal to cosine of its complement, because pi over 2 minus theta and theta are complementary because they added to pi over 2. So sine of 50 equals cosine of 40. Sine of 30 is cosine of 60. Cosine of 10 is equal to sine of 80, so on and so forth. And it's true either way you say it. That's what's going on there. Cool? Easy peasy? Now, what's really great, like I said, is all of these things are fantastic to know. You already know these two things. You just didn't know it. You'd never seen it written in formula format. You just saw me doing it with triangles, but you already knew that. You saw me reflecting things over y-axis. You saw me reflecting things over x-axis. And I don't know if you knew this about sine and cosine being complementary, and that's why it's called cosine. It's literally complement sine. But there it is. What's that? No? Yeah, it's a shame that it's not said. They're actually called co-functions, sine and cosine, because they are complementary of one another.
So why are
Secant and cosecant are co-functions.
right?
Tangent and cotangent are co-functions. What do you mean?
Well, in this case, it's quite literally complementary.
No, it always means quite literally complementary.
Right.
Secant and cosecant are complementary of one another.
I guess I was asking.
I think you're trying to talk about the relationship between reciprocal functions.
Yeah.
Yeah, so sine and cosecant are reciprocal functions.
Yeah.
Alrighty, so we're just going to do some simplifying here. You ready? 3 cosine of theta plus 4 cosine of theta. What do you think that simplifies to? 7 cosine theta. Yeah, don't overthink this. Boom, there it is.
I made sure that it would make some sense.
Yeah, that's why you said 12, yeah.
Yeah, I didn't want to say like 17. But it
Tangent alpha minus 3 tangent alpha. Hope nobody's brain breaks. Negative 2 tangent alpha. Oh, she left! She's gone!
Did you see anything move?
No, it just turned off. Oh, she might have timed out. Dylan, did she pop on? Like, did her face show up at all, or did she just leave? I hope it timed out. I hope she's asleep. Yeah, one of my 8th period students in advanced pre-calc, Michael Burns, he missed a class period one day, and then he sent an email to his end of the day teachers, and he was like, "Yeah, so I just woke up at my desk. It's 3 o'clock." Apparently, he fell asleep during lunch and just never woke up. Missed the whole rest of his day at his desk. He wasn't even in his bed. He just like put his head down and passed out. Woke up at 3 o'clock at his desk still. Like, yep.
Mr. Hutchins, when I was late to your class for coronavirus, I passed out at my desk.
Yeah. It's funny. It happens, you know. All right. Is there a back to these? Yeah. Okay. Sine negative theta plus 2 sine theta. Well, sine is an odd function. So sine of negative theta is the same thing as saying negative sine of theta. And negative sine theta plus 2 sine theta is just sine theta. By the way, I love trig manipulations. Absolutely love them. Well, so far, yeah. Alrighty, let's see what's going on with part B. Well, let's see. This says 90 minus an angle. So cosine of 90 minus an angle sounds to me like I would be getting a complementary angle, right? So that sounded like sine of theta over, and let's see, cosine is positive in quadrant 1 but negative in quadrant 2. So this is saying take your triangle that would have been in quadrant 1, reflect it into quadrant 2, you're going to get negative cosine of theta. And since sine over cosine is tangent, this is negative tangent theta. I'm writing in too much purple. Let me move over to green. I love trig manipulations. So this one, what I see here is something that factors with a GCF of 2. And 1 minus sine squared theta. That's cosine squared theta. But where did that come from? Well, let's remind you that sine squared theta plus cosine squared theta equals 1. So if you wanted to get cosine squared theta alone, you would just subtract sine squared theta from both sides. Ta-da! So that's why the answer is 2 cosine squared theta. I just subtracted sine squared theta from both sides.
How did you get cosine squared minus of the sine, like on the higher part?
I'm showing you that's where it came from. Here's the Pythagorean identity. And if you want to get cosine squared theta by itself, you just subtract sine squared theta from both sides and you get that. So the 1 minus sine squared theta, I just replaced it with cosine squared theta.
I need to examine this for a little bit.
You do that, but I'm going to move on. But by the same logic, though, this is also a true statement, which I didn't use. But it's also true. It's just getting the trig by itself, just subtracting it from both sides of the equal sign. So for part B of this example, what I'm seeing is, again, a GCF. I'm seeing that these can both give up a sine theta. So it's going to give me a cosine squared theta plus a sine squared theta. And, oh look, cosine squared theta plus sine squared theta. That's equal to 1. So it's just sine theta. So all of that mess equals sine theta. Very satisfying. I should start an ASMR YouTube channel where I just do trig identity manipulations the whole time. And at the end, you just get really cool, elegant crap and just watch the math goosebumps. I should.
I would watch that.
ASMR. I got to do it now. I'm gonna really do this now. I'm doing it.
It's like someone goes to check the notes one day and it's just not instead.
Okay.
Oh no, you just do it.
Expand and simplify. You have to FOIL this. Please don't say cosine squared minus sine squared, because that's not at all it is. You have to FOIL this out. What you're going to get is cosine squared theta minus 2 sine theta cosine theta plus sine squared theta. But what happens if you do cosine squared theta plus sine squared theta? What are those two things? Yeah, they equal 1. I just boiled and combined like terms. I just didn't show all those steps, but that's what you would have gotten because they would have been 2 of the minus sine theta cosine thetas. So what you end up here, it is 1 minus 2 sine theta cosine theta. What don't you get?
I just never learned how to boil. I still use Planet Square.
Oh, here. Just what? No. Just watch. No, watch. Watch. Cosine times cosine. Cosine squared. Cosine times negative sine. That gives me negative sine theta cosine theta. And then negative sine theta times cosine theta gives me a second negative sine theta cosine theta. So those two things would have been in the middle combined like terms. And then negative sine times negative sine positive sine squared.
So how does first outer inner last make sense?
First one times first one. Outside one times outside one. Inside times inside. Last one times last one. That's what they mean by that. It basically it is a Punnett square without drawing the squares. And you know what really pains me? This is also an identity that we won't know till tomorrow.
I was gonna say that looked familiar.
It is. It's sine of 2 theta.
Okay.
But that's one of the double angle formulas, which are all in the reference sheet.
No, actually,
Factor. Hey, look, the difference of two squares. It factors instantly. Which, by the way, this is also that's cosine of 2 alpha. But that's not what we were told to do. Cosine alpha plus sine alpha times cosine alpha minus sine alpha. There, it's factored. Done. Now for part B. A difference of two squares is always pretty easy. Now part B, this is like a trigonometric quadratic, if you want to think of it like that. Imagine, instead of what you see here, imagine it says x squared minus 3x plus 2. So, I mean, you can. So we're like basically just like let x equal tangent theta. If this helps, then do it, you know? And then you're trying to factor this thing, and you go, okay, I'm looking for two numbers that multiply to positive 2 that add to negative 3. That's negative 1 and negative 2. So it will be x minus 1 times x minus 2. But, oh, wait a minute, it's not x. It's tangent theta. You see, writing it like this and being able to factor would give you the ability to solve trig equations. So I could have set this thing equal to weird stuff, and you would have been, well, let's just say it equals 0. You'd have been able to solve for theta by factoring. Whoops, just threw my pencil or pen. Pretty easy. Trig manipulations. Alrighty. You think if I made trig proof videos,
People would probably watch.
would people watch them? But it would almost be, I would want to do it as like,
you have to do all math. I don't think
No, like you could literally just do like a video of like this worksheet and tell the people to watch.
yeah, but I don't mean, I just mean, no, I mean like not jokingly ASMR obviously, but like
Yeah.
just like this is the trig proof channel, you know, just do trig proofs.
That would be so
Trig
cool.
proofs all day.
You can use all the profits and
too much of a
investment.
niche.
What's that? Yeah.
So you have to do math as a whole, because I see people that watch math as a whole, if you found any kind of.
Oh, well, I mean, those videos already exist. Those channels already exist. That's the problem. Even that, now you're not special, you know. But you know what? But if I was doing a trig proof and in the top right hand corner there was it was like somebody cutting a bar of soap, you know, at the same time. If I could get people's brains to think like every time they're doing a trig proof, if they can have that really satisfying reaction, just like
That'd make you a better
just
math teacher
would
for the world.
yeah, it would just make you like Condition them. Thank you. That's where I was looking for. Like, condition your brain to want the end result. Like, oh, sine of x. You know, like you just like you really want it. You know. Anyway, cool. It says simplify. So basically, take all the crap that we've done so far and put it to one question. So this 2 minus 2 cosine squared. Yeah, that factors. So is 1 minus cosine squared sine squared? Yes. But that is not what you want to do here. And here's why. Because 1 minus cosine squared is the difference of two squares. And one of its factors is right there. So what you would want to do is you would want to factor the 1 minus cosine squared into 1 plus cosine theta times 1 minus cosine theta. That way the 1 plus cosine thetas will cancel off of the top and bottom. So you get 2 minus 2 cosine theta. I mean, you could also leave the 2 on the outside, so it's 2 parentheses 1 minus cosine theta. I just decided to distribute it because why not? And the last one. The bottom happens to be the difference of two squares that we already factored right here. So just going to do it again. And cross off the top and bottom like that. You're left with 1 over cosine theta plus sine theta. And that is it, folks.